Welcome to The World, the Universe and Us, the weekly news podcast from New Scientist. I'm Dr. Rowan Hooper.
And I'm Dr. Penny Sarche. On today's show, we look at a new study linking 140 different revolutions and rebellions to historical changes or disturbances in the climate and the environment. And we hear about a new form of deep brain stimulation technology that could improve the way we treat a range of conditions.
We're going to start with the discovery of an organism that's able to live for astonishingly long periods of time. And it's so long, I think it begins to challenge really the concept, the meaning of what it is to be alive.
Well, that's exciting. So I'm thinking stone pines live for a couple of thousand years. Are we talking that kind of thing?
More.
5,000, 8,000?
100,000 years.
100,000?
This is a microbe found in the permafrost in Siberia.
Wow.
That's stayed alive for at least 100,000 years. And so this isn't a colony of things growing that sometimes you get very long-lived colonies of things. This is an individual cell, individual cells that have managed to stay alive through this long without dividing.
That's amazing. I guess I have a lot of questions. Is it frozen? Is it really alive? But first, how long did we think microbes could live until this point?
Well, we thought they could live quite long, and there's a lot of theory about how long, the minimum amount of energy a cell would need to survive. And then there's been some microbes collected from ancient sediments and salt crystals, really good kind of capsules to keep things for a long time. And also then there's the way of reviving them. You can get a microbe from a marine sediment or something that's very, very old, and revive it, and that might be up to even 100 million years old. So we all that's to say we do suspect there's lots of very long-lived microbes out there. But this is what I mean. This is the crux of it, is that you can get into a sort of suspended animation state, of dormancy. Sometimes it's a spore, but is that alive?
Yeah, if something needs reviving and otherwise it's just not really doing anything for 100,000 years.
Yeah.
So how, as a scientist, then, do you go about asking this kind of question, proving something has been alive for 100,000 years? It's
without a TARDIS to go back in time.
Yeah, exactly.
Well, I mean, 100,000 years, it's, you can't run a lab experiment that long. Our reporter on this story was James Deneen. He spoke with Karen Lloyd at the University of Southern California, and she talked about the trouble of experimenting with time over this range.
It's the weirdest variable to work with, because normally if I want to say, yes, life can grow at 100 degrees Celsius, then I put something at 100 degrees Celsius, I put the organism in it, I count the cells before I put it in, and I count them afterwards, and I see that there's more of them. End of story, no question, not a hypothesis, I've shown it.
So to get around that problem, the researchers went to look for microbes in places where they knew there hadn't been any change for a very long period of time. And the reasoning, of course, then is, they must be as old as that surrounding environment. And so they went to the Chukchi Peninsula in the easternmost edge of Siberia, drilled into the permafrost and got some sediment from there. And that's known to have frozen between 100 and 120,000 years ago. So that's it. Anything from there has been there that long.
So if anything's living in that ice, it's as old as that ice. But is it really living?
Well, that's the thing, proving it's alive.
So how did they go about doing that then?
Well, so what they did, they got the sediment, they extracted all the DNA out of this gunk, basically, and reconstructed the genomes from whatever they found in there. And there are loads of different things in there, but some of it, well, they didn't know what was from dead DNA and what was from these cells that might still be alive. So they had to figure out a trick to distinguish between those things. And what they did was add an enzyme into the mix that repairs degraded DNA. And then they did the genome reconstruction again. And they found that most of the reconstructions got much better because the DNA had been repaired. But for 6 species, the reconstructions didn't really change very much, which implies that, if you're still with me, that the DNA wasn't degraded to start with. So, in other words, it had been maintained by the cell during that whole period of time. That, in other words, it was alive.
Clever. I like the trick. It feels like a bit of a jump. Like maybe there could be other explanations. Like for some reason that DNA was just better preserved. But it's exciting to think that there are these organisms that were over this very long timescale still maintaining the integrity of their DNA, like actively.
Yeah. Well, actively, if you like we think sloths being really slow.
Yes.
That. A sloth is super active compared to this thing. Like this is so slow, but it is active in a sense.
Amazing. So what were these 6 species then that seemingly still had intact DNA?
Right. So this is where it gets quite exciting.
Yeah.
They're from the a phylum called Promethearchaeota, which is sometimes called the Asgard Archaea.
The Asgard Archaea.
The Asgard Archaea. They're considered to be the closest living relatives of eukaryotes. That's the domain that we all belong to, and also all plants, fungi, protists. And they are exciting.
Yeah, we don't know that much about them yet, but they potentially could give all kinds of clues to our own origins, which is very cool.
So just to tell more about the Asgards, because they are so cool.
Yeah, and how they got their name again.
Yeah. Well, so it's from a site in between Svalbard and Iceland in the sea there in a hydrothermal vent. And when this submersible was sort of trolling around down there, it came across this kind of city of sculpted pyres and towers, and it was Norwegians controlling this submarine, and so they called it Loki's castle after Loki, the god of mischief, and they sampled from there. And when they sampled microbes that they'd got from Loki's castle, they found these organisms that weren't archaea and weren't bacteria, but looked like a stepping stone between archaea and eukaryotes, and between us. So they called them the Asgard Archaea. You do get them everywhere, all around the world, but they're called the Asgard Archaea because that's where they were first discovered, in Loki's castle.
Okay, so that's where they were first found, but we're going back to Siberia now.
Yeah, back to Siberia. And when they looked at these things from Siberia and looked at key genes in these organisms, they found that these key genes weren't that different from other Asgard Archaea found in other places.
So living freely outside of the permafrost.
Right.
And
So that has more implications. And here's Karen again.
They're just normal. They're like the most boring Asgards in the world. And I was like, Ring Sing, this is the best result you could possibly get. The fact that they're boring, the fact that they're distributed across all the Promethearchaeota, I got to work on how to say that word. It implies that this is actually just a normal function of the group.
The ionophily is just something they can all do if they find themselves in some frozen marine sediment.
Yeah. Or if they find themselves in non-frozen marine sediment. I mean, we kind of already know that they tend to hang out in these places that ionophily should be functioning. But this finding them in permafrost and finding so many of them, and ones that just don't look any different than all the rest of them, implies that this is just what they do.
So in other words, what they're saying is that being able to survive for these huge stretches of time might actually be quite a common trait to species that are in this whole branch of life. Karen has coined a word for it. She calls them ionophiles. She pronounces it differently, but she pronounces it wanophiles. But that means you like wine. Right?
Oinophiles, if I remember my Greek.
So eon, like an eon of time. Ionophile is something that loves long time. It's like extremophiles that live, like thermophiles that live in extreme environments. Ionophiles are these that extremely slow growing, very long lived microbes. And here's Karen again.
If we want to start looking at lineages and ionophily as an adaptation, not as an accident, and what role has long-livedness played in evolution, in deep evolution, then finding these things in such high diversity in a place where we can be pretty confident that they really were just sitting there and nothing really moved in or out and fed them, or they weren't able to disperse during that time, that really helps us to link it to this particular group and how this evolutionary mechanism possibly has worked within that group.
So, as you sort of alluded to, Rowan, this discovery potentially sort of challenges what it means to be alive. Yeah. Is dormancy being alive? Is repairing your DNA once every 1,000 years life? Yeah.
Is it life as we know it? I don't know. I mean, if you do nothing for tens of thousands of years, does that count?
So when we came into this story, I was skeptical. I was thinking they're not alive. They're on ice and they could be revived maybe.
Yeah.
But now I think about it, repairing DNA, if that is what they're doing, that is a cellular process. That is like being alive.
Yeah, just very, very slow. I think it does expand. So we know that life is it's a very fuzzy concept. We can't define it properly.
Yeah.
It's not a binary switching a light on and off switch.
No. Yeah.
It's not one thing or other. But it is weird to think that it's a broad thing that life is. And we've talked about it on the podcast before, when people are in near-death experiences and they go in and out of this phase. It's like sleep, going in and out of sleep. It's a fuzzy, broad concept. And I just think that these microbes, it's very cool that it's helping point to that, even at a cellular form, that they have this kind of fuzzy concept of life as well.
Okay, we want to talk about a potential breakthrough in brain implants now. As you may know, putting an electrode into someone's brain can help with a range of neurodegenerative conditions, things like Parkinson's disease, and then also sometimes conditions like OCD and epilepsy. But this deep brain stimulation is actually quite a crude thing to do. So a team at the University of California, San Francisco, has made an implant that is intuitive, for want of a better word. And the idea is that it knows when it's needed and turns on accordingly. And Alexandra Thompson is here to tell us about it. Alex, what is this being used for?
So it's been trialled on a handful of people who have what was considered to be untreatable chronic pain. And it's so sweet because one of the participants has even been able to hug his wife for the first time in years.
Wow. When you get medical breakthroughs like this that have a real human impact, brings it home, doesn't it? I mean, and chronic pain is an awful condition because in many cases it's just untreatable, isn't it?
It is, and it's also very common. So about 1 in 5 people have it. I mean, definitions vary, but a lot of people who have it just don't get relief from the traditional attempts to relieve their discomfort. So it might be because chronic pain can result from fundamental changes to brain circuitry, which is challenging to target and remodel with conventional therapies. And also the specifics can vary so much from one person to another.
Yeah, when you put it like that, it suddenly makes it clearer that why it's hard to treat. If it's changed the brain circuitry, then it may be, well, that's why it's so difficult to treat.
So has the sort of old-fashioned or traditional deep brain stimulation, has that been used before to try to treat chronic pain?
It has been. It's not widely available. The problem has been that traditional, we call it DBS, which involves stimulating the brain using tiny electrodes, has very inconsistent results because it tends to be a constant stimulation. And also the same brain areas are targeted. It's like a one-size-fits-all approach. And we know from evidence, previous research, that pain arises from different circuits in different people.
Yeah, it's a really sort of individualised thing. That's why it's so hard to treat.
Exactly. But here you have an intuitive implant that was mapped to an individual's specific, for want of a better word, I suppose, faulty brain circuitry. And then it could detect in real time when they were in a considerable amount of pain and could time the stimulation accordingly. And then you get a much better treatment.
So that use of the word intuitive, we're hinting at artificial intelligence, machine learning, that kind of thing here, are we?
Yeah, so this is machine learning that could identify and distinguish between the electrical activity that occurred when they were in high levels of pain compared with low or no pain, because it's not always a constant chronic pain. It can ebb and flow. So it's a small trial at the moment, but what happened was over 10 days, 6 people with untreatable chronic pain underwent intracranial electroencephalography, in which electrodes recorded from or stimulated 14 sites across the brain. So for 5 of the people, researchers were able to identify both the brain regions and the frequency of stimulation that provided the greatest pain relief. And then the next stage was the machine learning. So that was when they sort of personalised it. And then finally, the team could implant permanent DBS electrodes into each participant, which was personalised to their brain activity and could deliver optimal stimulation whenever pain-related activity was detected. So there was about 6 months of fine-tuning, and then it was put to the test in a sham-controlled trial. So participants either had the stimulation turned on or turned off, and they didn't know. So on average, the real stimulation reduced their daily pain intensity by 50%, compared with an 11% increase with the sham. Daily step counts rose by 18% with the real thing versus 1% with the sham. And the real thing also was linked to fewer symptoms of depression and less pain that interfered with their daily lives. And also these benefits, they weren't temporary. This persisted over a follow-up of 3.5 years.
God, you wouldn't want to be in the sham group, would you?
No, I think everybody got it. It was just sometimes turned
Oh, I
on and
see.
sometimes turned off.
Oh, okay.
Yeah,
Oh.
I don't think they give you brain surgery and not put a real thing in there.
No. Okay. But 3.5 years, that's good, because I always thought that the effectiveness of deep brain stimulation wore off after a while with the electrodes.
Yeah, don't the immune cells start sort of attacking the implant?
That can happen. There can be mechanical damage. It can be as simple as that. Batteries need replacing. It can also be disease progression, even scarring in the brain tissue. But also they can last for 10 years.
Wow.
Yeah.
So it's interesting that they started with chronic pain. That's obviously this horrible condition and often untreatable. But we talked at the top about how there are other conditions where DBS is sometimes used. And there are things like Tourette's and epilepsy. But is it being looked at for other things as well? Dementia, depression, addiction?
Yes, and depression's sort of particularly emotive because we did a story last week about a man who said he got his joy back after being severely unwell with depression for decades.
That's another story that really got me.
Yeah.
It was like he'd been hospitalised. He'd basically had awful, untreatable depression for years and then experienced joy for the first time. It's just the most amazing story.
Yeah, it was really lovely. And also it's being tried for obesity, but it's that's much more of a trial kind of explorative stage.
How do we sort of see that working for obesity? Do we still need things like that now we have Ozempic and similar drugs?
Well, not everyone responds to drugs like that.
Right.
And I think the average weight loss is in the sort of 10-15% mark in trials. So if somebody has severe obesity, that might not take them to a healthy weight. And also there's supply issues. I think in the UK you can have it for 2 years and then you have to readdress what your treatment options are. So definitely still a space for other treatments.
Alex, when you were saying earlier, we were talking about how chronic pain changes the brain wiring effectively. I wonder if that's how psychedelics have had some success in treating some of these conditions, because they kind of force a rewiring in some sense, don't they?
Yeah, and we're working on another article, hopefully be out very soon, where a single dose of the psychedelic compound psilocybin was found to remodel connections of a specific brain network.
A single massive dose. No, maybe single normal dose.
New Scientist does not endorse this message. It's really exciting, isn't it? Because so far with things like drug treatments for chronic pain and also depression, it's kind of using the tool that you've got to try, you're basically messing with chemistry to treat what actually fundamentally is something to do with neurons and brain activity. And this is actually a way to try to target the underlying problem rather than hoping the chemistry fixes it.
Yeah, that's a great way of putting it, because sometimes there isn't an obvious problem to be fixed with pain. It can be sort of an overdrive in the brain, so it's getting to the root of it.
And the thing that struck me with that depression story was about a third of people have treatment-resistant depression, right? And the antidepressants aren't working. So this kind of thing could have real promise, you'd hope. Okay, here's a question. If I asked you what caused the French Revolution, what would you say?
Je ne sais pas. I don't know. Well, I would say, inequality and resentment and let them eat cake.
Yeah,
and,
that can't have helped, right?
No, it can't have helped. Rebellion against the rich and the elite, I would say.
But what also about volcanoes and sunspots and the little ice age and the...
that wouldn't have been on my list. No. Okay, so this is about the effect of climate change and environmental change on social unrest.
Yes, it is. So this isn't just the French Revolution, but rebellions and revolutions across Europe in general in the years of the Little Ice Age. That took place between 1250 and 1860 AD. And an analysis of 140 of these rebellions, that sounds like a cool database, finds a correlation between things like volcanic eruptions and reduced sunspot activity and surging food prices.
Well, okay, so this immediately reminds me of the Arab Spring,
right,
which we know that environmental conditions had an impact there. There was a really long drought in Syria in the years leading up to the Arab Spring 2011. And obviously they had a repressive regime to push back on as well. But climate change has been implicated in that as well.
Yes, exactly. And so now a team involving scientists at the University of Toulouse in France has examined 140 rebellions and revolutions from this time in Europe. And this was one of the most severe periods of weather experienced over the last millennia. It gripped parts of the Northern Hemisphere, especially Europe and North America. So during this 600-year period, it was anomalously cold. Temperatures dropped by an average of 1.75 degrees Celsius, can have a real impact on crops. And so too the precipitation. It fell by as much as half. So agriculture at this time was just thrown into chaos.
Well, this is when the Thames froze over, didn't it?
Oh, yes.
The Thames
that
froze
beautiful
regularly.
picture.
There were frost fairs on the Thames.
Yeah.
And parties on the Thames. You'd have to party
well,
to keep
that bit
warm.
sounds fun, but but for this study, the researchers basically overlaid episodes of social crisis with things like solar activity, volcanic eruptions, climate change, and they also looked at what was going on with the grain and bread prices at the same time. And they found that cold phases of the Little Ice Age, so the particularly bad bits of the Little Ice Age, were correlated with significant increases in rebellions.
Okay, correlated, not caused.
Not caused, exactly. No. And we'll get to that in a bit. But it is quite compelling that they found when temperatures fell, whether through sunspot decreases or volcanic activity, when they fell to anomalously low temperatures, this was associated with an extra 0.72 rebellions per year. Nice science there. With similar results for rainfall reductions as well.
Okay, so this is like a bit like the Arab Spring when so agriculture got clobbered, wheat production fell, grain prices spiked 2007, 2008. In Egypt, bread prices went up 37%. So, lots of factors contributing there.
Yeah, and some people sort of originally, when the Arab Spring was just starting, they were referring to it as bread riots. But this influence, the climate drought influence on wheat production and price of bread, is what strategy people call a threat multiplier. And in this new study, the team found that the highest number of rebellions and revolutions was associated with spikes in wheat and barley prices, up to 1.16 extra rebellions per year.
Wow. Well.
So they say that while climate did not directly lead to rebellion, environmental conditions led to this cascade of events which led to food shortages. And then you can see those food shortages evidence in the increasing grain prices. And then, of course, that in turn can lead people to rising up against authority because they're hungry. And they need to.
I mean, there's an obvious thing here, isn't there? It's happening now more and more.
Food prices are rising and rising.
Yeah. And we're talking historically, but it's going to be even worse going forward.
With climate change.
And the CIA have known this. They had they had a long-running program looking at the effect of climate change on conflicts around the world. They're really well aware of this stuff.
Yeah, I'm sure we've been reporting on it for
years we have,
at New Scientist. As the researcher David Kanievsky put it, scarcity of food is like a parched forest after a long drought. When you add political or social grievances, then it can ignite revolt. So their work shows that one of the most extreme periods of upheaval was following the eruption of Iceland's Laki volcano in June 1783, if you remember. And so that led to higher levels of sulfur dioxide in the atmosphere, which, as we know, can lead to cooling.
Yeah.
The team suggests that following this period, from 1788 to 1798, there was a peak of 1.4 rebellions annually, including the tumult of the French Revolution.
Wow. So it wasn't just Marie Antoinette.
No.
It was a volcano.
Not entirely down to her, no.
And obviously we're going to see a lot more of this.
Well, that's the fear, isn't it, with climate change? That link between climate and rebellion and revolution, as demonstrated in this study, is correlation, not cause. But it's definitely a threat multiplier.
And we hear a lot about our capacity to be resilient. And I do worry that we don't have much capacity. We're brittle, and our capacity to, absorb different threats is maybe quite thin, which is quite worrying.
Yeah. And on that note,
sorry,
that's all for this week. You've been listening to The World, the Universe, and Us.
Do go ahead and subscribe. Spread the word about our show, please.
Thanks for listening.
See you next week.
Bye.
Bye.